Hi everyone, my name is Mubashir Shamim from the CS Department of Sri Venkateswara College of Engineering. Today we gonna discuss about Introduction to Mathematical Induction. Mathematical induction is a powerful technique for proving statements about natural numbers. It involves demonstrating that a statement holds true for the base case and then showing that if the statement holds for a particular value, it also holds for the next value. Principle of mathematical induction. Fundamental idea. The principle of mathematical induction is a powerful logical method used to prove statements or propositions that are true for all natural numbers. Step-by-step approach. To prove a statement using induction, you must establish a base case and then show that if the statement is true for a certain number, it is also true for the next number. Broad applicability. This principle can be used to prove a wide range of mathematical statements, from simple arithmetic identities to complex in computer science and combinatorics. Base case. The base case is the starting point of a mathematical induction proof. It establishes the truth of the statement for the simplest or smallest possible value of the variable. Typically, the base case involves verifying the statement for n equal to 0 or n equal to 1, as these are the most fundamental starting points. Proving the base case is the foundation upon which the entire inductive argument is built. It ensures that the statement holds true for the initial condition before proceeding to demonstrate the inductive step. Inductive step. Hypothesis. Assume the statement is true for a particular value of the variable such as n equal to k. Inductive argument. Use logical reasoning to demonstrate that if the statement is true for n equal to k, then it must also be true for the next value n equal to k plus 1. Proving the claim. Combining the base case and inductive step to conclude that the statement is true for all values of the variable. Proving statements using induction. Mathematical induction is a powerful technique to prove statements about natural numbers. The process involves establishing a base case and then showing that if a statement holds for any arbitrary number, it also holds for the next number. By repeatedly applying the inductive step, you can systematically prove that the statement holds for all natural numbers. This method is particularly useful for demonstrating patterns and relationships in mathematical expressions and algorithms. Induction on natural numbers. The principle of mathematical induction is particularly useful when proving statements involving natural numbers, the non-negative integers 0, 1, 2, 3, and so on. By establishing a base case and then showing that the statement holds for all large natural numbers, we can conclusively prove that the statement is true for all natural numbers. Induction on natural numbers follow a clear logical progression. We first verify the statement is true for all the cases of 1 or 0. Then show that if the true of for some arbitrary natural numbers n, it must also be true for the numbers n plus 1. The process can be repeatedly, identically to prove that the statement holds for all natural numbers. Induction on integers. Extending the principle. The principle of mathematical induction can be extended to prove statements about integers, both positive and negative. This allows us to establish patterns and relationships that hold true for the entire set of integers. Proving divisibility. Induction on integers is often used to prove divisibility properties such as showing that the sum of any consecutive odd integers is a perfect square. Establishing inequalities. Induction can also be applied to demonstrate various inequalities involving integers, like showing that the sum of the first n positive integers is always less than n power 2. Recursive definitions. Induction on integers is crucial for understanding and proving properties of recursive definitions, which are commonly used in computer science and mathematics. Induction on sequence. Defining the pattern. Identifying the underlying rule or relationships in the sequence. Base case. Verifying the statement holds true for the first term of the sequence. Inductive step. Prove that if the statement is true for any arbitrary term, it is also true for the next term. Mathematical induction can be used to prove statements about sequences where we can need to demonstrate a given property holds true for all terms in the sequence. This involves establishing a base case and that if the property holds for one term, it will also hold for the next term, thereby proving the statement entire sequence. Applications of mathematical induction. Proving formulas. Mathematical induction is commonly used to prove mathematical formulas and identities such as the sum of the first n natural numbers or the formula for the nth Fibonacci number. Analyzing algorithms. Induction is essential for analyzing the correctness and time complexity of algorithms, helping computer scientists design a more efficient program. Verifying hardware. Engineers use inductive reasoning to verify the correctness of digital circuits and computer hardware, ensuring reliable and secure electronic system. Rigorous proofs. Induction is a foundational proof technique that allows mathematicians to establish with a high rigorous proof. Conclusion and key takeaways. Summary of key concept. Mathematical induction is a powerful proof technique for establishing the validity of statements involving natural numbers. It consists of verifying a base case and then showing that if the statement holds for some numbers, it also holds for the next number. Wide applicability. The principles of mathematical induction can be extended beyond natural numbers and have applications in computer science, mathematics, and many other fields for proving the correctness of algorithms, identities, and more. Importance in computer science. Induction is particularly crucial in computer science where it is used to verify the correctness of recursive algorithms, data structures, and other fundamental concepts. Continued learning. Mastering mathematical induction takes practice. Continued exploration of applications will depend on your understanding and unlock its full potential in your problem solving.